Hi friends, so today we start lecture 59 in our helicopter dynamics course, and today I'm going to discuss about stability analysis methods for constant coefficient systems. So we are going to generalize some of the things we discussed in our previous lecture for the flapping blade equation to a more generalized system which you will typically encounter in realistic problems where you consider all the degrees of freedom, for example flap, lag, pitch and so on. I'm Dr. Ranjan Ganguly. Now, we have seen that whenever you are doing any dynamic analysis of rotor systems, you end up with periodic differential equations. And therefore, especially in situations such as forward flight, you get equations with periodic coefficients because you move the motion dependent forces to the left hand side, and then you have terms which involve sine psi, cosine psi, and so on. So, this is certainly a very complicated problem, and we are going to discuss it later. But it's very important to remember that whenever you are in forward flight, the equations of motion do contain periodic terms on the left hand side of the equation. But we have seen that hover case is a simpler case where you essentially get constant coefficient equations. So this is not only typical of the case here in helicopter dynamics, but in many structural dynamic systems, you essentially have constant coefficient equations of the type spring mass damper systems. So if you recall, the equation was beta double star plus gamma by 8 beta star plus nu beta square beta equals 0. So that equation had constant coefficients in terms of the coefficients of beta double star, beta star and beta. That's what we mean by constant coefficient differential equations. So now let's generalize this concept. So let's say you have many degrees of freedom. In that case, your system would look something like this. You would have a mass, stiffness, and damping matrix, and you would also have a force vector. So essentially, this is the general equation for a multi-degree of freedom spring mass damper system. There are n linear differential equations with constant coefficients. So constant coefficients means that m, c, and k contain only numbers. They do not contain any functions of time. They do not contain any functions of psi. So if we take a closer look at this system, we clearly see that the mass matrix, the stiffness matrix, and the damping matrix are all n by n systems. The force vector is a n by 1 vector, and q involves the degrees of freedom for the particular problem. So that's the differential equation we are concerned with. Now, one of the things which is done in any stability analysis problems, and those of you who are familiar with control theory would know that, is that we take a second order differential equation of this form and we rewrite it as a simpler equation which has only one derivative. Okay, so let's define this vector q as q dot. So essentially this vector size is now 2n into 1. Now the equation here can be rewritten as this equation. So if you look carefully, the first equation is simply q dot minus q dot equals 0. The second equation is mq double dot plus kq plus cq dot equal f. So it's the same equation, we have just written it in this form. And the reason to write it in this form is that we are now going to define this vector here q dot as y and this vector q dot q double dot as y dot. So we can write a equation system in that form involving y dot and y. So that equation would look something like this. So what we do is if we write the previously shown equation in matrix form, you get an equation of this form here where you have the coefficients of these two vectors, and again you can clearly see these are constant coefficient matrices. Here I is the unit matrix, so it's got unit diagonal and rest are 0, and 0 is a null matrix which is essentially all 0. and the size of these matrices is now 2n by 2n, and the size of this vector is 2n by 1, the size of this vector is 2n by 1. So we will now start thinking of this system as y dot equals a y plus g, provided we take this matrix involving I and n to this side. So essentially we have to take the inverse of this matrix and pre-multiply both the sides of the equation with that matrix. So if we do here, we get the equation y dot is ay plus g, and A becomes this matrix here, which is expressed in terms of m, k, and c. So all the information about the system properties is present in this matrix A. Sometimes it's called the system matrix. The vector G also has M and F, and so the vector G contains the information which is there about the forcing present in the system. So one of the points we should make at this stage is that these matrices will be there provided M is not singular, because you are calculating the inverse of M to obtain A and G, and therefore that should be present. So that's a requirement you need to check for. Now this particular form of the equation is very useful whenever you are doing a stability calculation for the system, because it becomes very straightforward, and I will show you that soon. So one of the things to realize is that stability of a system is an intrinsic property of this system. It does not depend on the forcing term. Therefore, to examine stability of a system, we set the forcing to be 0. And this is what we did in the hover problem, if you remember. And now we do it in a general problem. So if F equal to 0, G is equal to 0, because if you remember, G is expressed in terms of F. Thus the equation simplifies to this form: y dot is ay. This is a homogeneous differential equation. Now if we want to find the stability behavior of this equation, we can presume a solution in terms of exponential function e. Okay, and if we substitute this into this equation, we need to calculate y dot. So y dot would be y lambda e lambda t. So we differentiated this function here, and then we express this equation using y dot and y. So both sides we substitute these values for y dot and y. So we get lambda y e lambda t as y dot, and ay becomes a y e lambda t, and then I do some cancellations here, and then I obtain this value here. So the cancellation can be done because e lambda t is never going to be equal to 0. It's an exponential. So ay must be equal to lambda y. Now this you will of course recall from matrix theory that it's a simple eigenvalue problem, and therefore you can solve it using a plethora of solvers which are present in any higher level programming language such as MATLAB or Python libraries and so on. And then you can obtain the values of lambda for the system. You will essentially get 2n of them, and in general they will be complex. They may be real, but for generality let us assume that they are going to be complex. Now each of the eigenvalues can be expressed in this form: lambda k is alpha k plus I omega k. Now this is for the kth case. So here now let's look at both these parts. The first part, which is the real part, this represents damping. The imaginary part, this represents the frequency. So one of the things which is very important is that if a single of these lambda k, a single of these lambda k has a positive real part, the system is going to be unstable. So that's a very important concept to remember. And it's important to know that any one of them would cause the instability. It's not that you need to have several of them and so on. So if a single of them has a positive real part, then that particular degree of freedom is going to be the cause of the stability problem. Now physically what this positive real part would do is that it would create a growth of the system in terms of the system response. So essentially it would blow the exponential function up. So very often in control theory and instability, we express this particular concept in terms of diagrams. So the diagram is known as the root locus. So essentially here we have plotted real part of this lambda k versus the imaginary part. And eigenvalues would be somewhere in this depending on whether they are real, whether they are complex and so on. If they are real, they would be lying on the axis here. So y would be 0 for those values. But in general, they may lie at some point here if they are complex. So there would be a complex conjugate pair. Now, whatever is in the left half plane is stable. That's very important to remember. And whatever is in the right half plane is unstable. So if you do the calculation for a system, find the eigenvalues of the A matrix and all of them lie on the left half plane, then you have a stable system. And if a single of them has come into the right half plane, you have an unstable system. So that's a very easy check for stability of linear constant coefficient differential equations. So we will see that in several conditions in rotor dynamics, we can use this kind of theory. It's not just in hover condition, but also in certain low speed forward flight conditions, we can approximate a matrix by taking a mean value. But if we cannot do that, then we have to resort to a more complicated theory known as Floquet theory for periodic differential equations, which we will discuss later on in this course. See you then.